Gail's a professor in physics. Gail is also our most recent SCHEV Outstanding Faculty Award winner. I think you may have seen something about that on the website, so congratulations, Gail.
Thank you.
Well deserved. Gail also, apart from having spent time as the chair of the physics department, has recently done a stint at the National Science Foundation as a program director in charge of the program there in her area. And that's, it's a big job. I know that from personal experience, just how much time and effort goes into those kinds of jobs. And thank Gail for doing that and bringing her expertise back. But more relevant to today, Gail has spent a lot of her 20 plus years, I believe, 20 years, and now in teaching large classes, teaching large introductory classes, especially for non-majors, but biology students, athletic students and the like. And is going to share with us some of her techniques today for keeping those students engaged in the large classrooms. Her research is in experimental nuclear physics, involves building large particle detectors at the Jefferson Lab, and Gail was very much, along with her fellow faculty, was very much involved in setting up the Center for Accelerated Physics that we now have, and that collaboration, strengthening that collaboration with the Jefferson Lab. So we're looking forward to hearing what Gail has to share with us today, and I'll hand it over to Professor Dodge.
So I very much appreciate the opportunity to talk to you today, and my hope is that I can tell you a little bit about what the problem is, although I'm sure everyone already knows what the problem is with keeping students engaged in large lecture halls, and something about the different things, a kind of a review of some of the things we've tried in the physics department to keep those students engaged. But I do have a number of concerns and topics where I would like to ask for advice from the audience about perhaps ways in which we can go forward to improve student learning. So I think that the problem is not yet solved, but let me just first go through and tell you a little bit about what the problem is, or what the problem was. So in physics education, Lillian McDermott is a very big name in physics education, and she pointed out many years ago, probably 25 years ago, that we have a real problem in terms of qualitative learning, conceptual learning in our students. And from her studies, she could tell that, in fact, students do not perform better on basic conceptual questions, qualitative questions, whether or not they've been instructed in courses with and without calculus. We're talking about introductory physics courses now. So whether or not those courses are with calculus, whether or not they come with a standard laboratory, whether or not the professor does demonstrations, and I'll do a demonstration at some point, and we all were invested in the idea that if we do demonstrations, that really helps student learning. Whether or not the classes are large and small, and most unsatisfying, regardless of the proficiency of the lecturer. So when I first became a faculty member at ODU, this is what I was told. We all go to these new faculty workshops in physics as new faculty members. They're held every year, and they're still held now. And the first thing they regale you with is how bad is the lecture and how impossible it is to have any effect on the students if you teach even the best possible job you can do. So this is sort of the ground. And another commonly quoted notation, the lecture is the best way of transferring information from the notes of the professor to the notes of the student without going through the minds of either. And I've heard that said to me many times. I tried to find the origin of that quotation, and I was unable to find it, but it's very widely quoted. And so the real issue is, how can we engage our students in these large lecture halls so that they think and actually learn the material that we think that they're learning? So 20 years ago, a book was published called Peer Instruction. It was by Eric Mazur, who is an atomic physicist at Harvard. He's not someone who does physics education, but he spent a fair amount of time trying to figure out how to improve his introductory calculus-based physics course, a large lecture course. And he published this book, which was widely available, I think even for free, to all faculty, so we could use this technique. And what it consisted of was, the approach he advocated is that you should not simply lecture to your students, but you should give them conceptual questions throughout the lecture to test their understanding. In other words, abandon somewhat the idea that everything should be solving problems and showing derivations and then expecting the students to go off and learn it. So what he did, and I'm going to point to the bottom here, a very key point of that is that he required the students to read the book ahead of time. And that's a point I want to get back to later on, but he would give a reading class at the beginning of a reading quiz at the beginning of class. Now he's changed it so that he has them do sort of an online response to the reading, and that response is graded and it's included as part of the grade. So the critical point is that if the students do some reading ahead of time, then you can spend more time in classes asking conceptual questions and seeing how the students respond. And it's pretty well known that the students can learn something from their wrong or right answers to these conceptual questions, and that learning is improved that way. And so what he does is he has this system where he poses a conceptual question. We'll go through an exercise like that in a minute. He asks the students to vote on the answer. Then they discuss it with their neighbors, and then they vote again. And in that process of discussing with each other and then voting again, they most of the time come to an improved understanding of the concept. So wherever possible, he combines this conceptual question with a demonstration, and he uses that feedback to determine whether to go on. In other words, do the students understand that concept or not? And if they don't, you spend more time on it. And he has this book consists of many, many, many questions that you can use in your class. And so when I first became a faculty member, we all started doing that. We would put these conceptual questions in our lectures, and we would, we hope, and I think we did improve the conceptual learning of our students. The students had pre and post testing with something called the Force Concept Inventory, which tests student understanding on a small fraction of physics concepts, or at least not half of the physics concepts. And the gain of the students was measured with this technique and without this technique. And of course, very large gains was seen by using this technique. So that is, that was the pedagogy 20 years ago, and he was not a physics education scientist. He was an atomic physicist, as I said, but this kind of swept physics education, and most people do incorporate this one way or another in their classes today. So let me give you an example of one of these conceptual questions that would be asked in class. This one has to do with conservation of energy. 2 billiard balls start to roll along a track at the same time with the same initial velocity. Which one will win the race? And this is an interesting question to ask students, because if they see this question and they already know something about physics, then they've learned that as something falls, its kinetic energy increases while its potential energy decreases, and then if it would go back up, the same thing happens. And so the student would immediately think, the ball has the same velocity here as it does here, right? But in fact, of course, for a while, the ball is going faster because it's down here, and so in fact, ball 1 wins the race. So even students who have been sitting in a physics class and think they know something about physics, even physics faculty, if they haven't thought about this in a long time, can get something like this wrong if they don't really think clearly about it. And so this is just an example of one of the kind of question that he would ask. I want to do one more example, and I want to do it with you. And this is the following. So this is a question that has something to do with Archimedes' principle, which essentially says that when you immerse something in a fluid, there's an upward buoyant force on that object that is equal to the weight of the displaced fluid. Okay, so we know that if you put a balloon under the water, of course, there's an upward force on that balloon. Okay. Another piece of information that's helpful to understanding this problem is Newton's third law, which the students would have had quite a bit earlier than this, which says that for every force, there's an opposite and equal reaction force. So if I push down on this table, the table is pushing up on me. And that's a very simple thing to say, but it's a very difficult conceptual problem in itself to teach that so that students really understand that concept. But nevertheless, both of those things are somewhat relevant to this question. So I would like to ask you to vote and tell me what you think the answer is. So the question is, if I put my finger in the water, what will happen? And I'm going to show it to you after you've all voted. So this water is balanced on this scale. And I'm going to put my finger down without touching the side of the cup or the bottom of the cup. My finger is going to be in the water. And I'm going to ask you, what's going to happen when I do that? Is this side going to go down, or is this side going to go down, or does it stay the same? So there's absolutely nothing to fear, and we try to make that very clear to our students. Again, I want to stress that this is the kind of thing which, a theoretical physicist, just to name one, could get wrong if they haven't been teaching an introductory physics class like this. It's one thing to know physics, it's another thing to kind of think quickly enough about it to figure out how it applies to this situation. So let me have a show of hands. If the finger is put into the water, what will happen? How many people think nothing? Half the class. How many people think that the beaker side, the water side, will go down? Smaller number. How many think that the beaker side will go up? So, okay. What you would really do in a classroom is you'd say, try to convince your neighbor. And this especially works if more than, say, half of the students get it right. But nevertheless, try to convince your neighbor of your answer, and then we'll take another vote, and then I will show you the result. Just to make it absolutely clear, my finger's not going to touch the bottom of the glass. Okay, it's just going to be immersed in the water. It's not going to touch the sides of the glass either, but it's going to be in the water. Okay, so how many people think A, nothing happens? Okay, about the same. How many think B, that the beaker side will tip down? Okay, that the beaker side will tip down. Okay, that's fewer than last time, I think. C, that the beaker side will tip up. That's about the same number. Let me put my fingers in, trying hard not to touch the sides or the... So, why did that happen? The reason that happened is because there's a buoyant force on my fingers, right? Because my fingers are immersed in a fluid, there's a buoyant force upward on my fingers. And if the water is exerting a force upward on my finger must be exerting a force downward on the water. Okay, so that's why I said you can use both those concepts together, help you get the answer right. Now, I think you can see that if students are sitting there in a lecture and they've had a chance to think and vote and think and vote, and then they see the answer, that is really, in my view, sort of the gold standard for teaching a concept, because you learn something from the concept that you now understand better. You learn something that you can't easily learn just from doing numerical problems. Now, of course, in practice, it's very hard to do every conceptual test with a demonstration, and we don't do that. We try to do demonstrations. It depends on how much time we have, but that is sort of the most powerful thing you can do to get the students engaged and have them really thinking about the answer to that and invested in the solution. We try to do that whenever possible. But so that's essentially the idea, is that by going through these conceptual questions, you learn the concepts better, means you're really learning the physics better. Now, of course, it gives you less time to solve numerical problems in class. And Mazur's research at Harvard indicates that he sees still an increase in understanding on the numerical problems. In other words, the regular homework problems where you have to calculate stuff and put numbers into equations. It's not as obvious to me that we see that, but it's, there's some debate in the community back and forth about whether there really is an increase in problem-solving ability, and I think the answer to that has a lot to do with what you make them do on the homework and how much time you spend doing other activities that are related to that. But I think it's quite clear that by doing conceptual questions in class, you help keep the students engaged and you keep them more interested in what they're learning. Okay, so what else have we tried? So I think many people kind of switched to this method way back when, and we have tried other things in the physics department. Of course, we've tried clickers. Almost everyone uses clickers these days, and I actually have a very high opinion of clickers. I think that they're very useful technique to record students' answers. I think it improves attendance, and you can give quizzes and you can get the answers back very quickly with quizzes. It provides a very fast way of administering a quiz in a big lecture course. So I really do have a high opinion of clickers. I think they make the class more interesting. They help motivated students learn, in my opinion. And by clickers, I mean you give conceptual questions where they use a clicker to answer it, and you can actually record their responses. You can give them credit just for participating, or you can give them credit for getting the right answer. You can give them quizzes and grade that as well. But I will say that there's a lot of overhead in keeping track of clicker responses from 120 students for every lecture in the semester. And so if you're going to assign credit based on clicker responses, then you can't just wing it and say, oh, well, I screwed up that day and I couldn't get the responses or whatever. If you're actually going to make part of the grade dependent on those clicker responses, then you have to have a way of dealing with when a student doesn't bring their clicker with them. So I would always have 2 or 3 extra clickers, and I'd have to write down the number and what the student was, and you spend a lot of time going into spreadsheets and correcting those scores if you want to use it in a grade. So it's very overhead intensive to use those, but I think valuable. And I think actually that's an example where the trade-off is worth it. Spending that time to do all that, in my opinion, is worth it in a large lecture course. We have the Physics Learning Center. This is sort of a drop-in tutoring center where students can come and get help. There are some pictures of it shown here. We have it staffed about 30 hours a week with graduate students and faculty and even some undergraduates. And the idea is that an introductory students can come, work on the homework, ask a question, keep working, and it's sort of an ideal environment for someone who needs a little bit of help with their homework. It costs a fair amount of time because most of us do this 1 hour a week, and there's some overhead in administering it. But I will say that not many students take advantage of it. I mean, this is my opinion. It is not something that students routinely, the good students, of course, will if they need it. So I haven't done a sort of a real check, but I think there's usually about 5 to 15 students in there at any one time. And a lot of those students are doing something, or not a lot, some of them are even doing something other than physics, or they're talking with their friends, or they're using it as a place to hang out before they go to the next class. So I think this is extremely good for the students who use it, and a lot of students don't use it. And that's sort of perhaps the theme of what I want to get to, which is that we have a lot of resources available for students that they're not using. And this is one of them. And it is something that costs us a lot of time. And I'm not saying for a minute, I think this is very, very good and we should have this, but most students do not take advantage of this. We have hundreds of students, probably, if you include astronomy, we probably have 1,000 students taking introductory physics in any given semester. And maybe 50 or 60 of them, or 70, 80, I don't know, let's say 100 of them are in this place at all in any given week. Okay, and I also want to say that some of them are purely focused on understanding better. Many of them simply want you to help them get the right answer to type into the box of their online homework. And that becomes so much the focus of what the students are trying to do that getting that right answer in that online homework box, that you can find that there's no time to, they sometimes are not interested in really going into depth about the physics that they did or did not understand. So that's an issue more related to how we deliver homework than it is to the Learning Center. So, okay, we have the Learning Center. We've also implemented Scale Up. I looked, I thought maybe there was a more recent one, but in fact we haven't had a provost conversation about Scale Up for years, so I thought I would just review what this is. This is another big wave that has swept physics education. It's a technique that's been adopted not only by ODU, but by something like 50 universities at least. And the idea is that you have a big room with round tables, and you seat your students, 9 people per table, around these round tables. They work in teams of 3 to do a lot of interactive problem-solving type activities throughout the course of the lecture. So the lecture is you still have to have them read ahead of time and come in knowing something, and you use your time in class not just to do conceptual questions, but also to have them do regular numerical problems that they can actually work on together and try to solve. And they work in these teams of 3, which is supposed to make it very interactive. And these teams of 3 are supposed to be very carefully prepared so that you have 1 student from the top third of the class, 1 from the middle third, and 1 from the bottom third in each team of 3. So you're supposed to assign all the seats to specific people based on the results of tests. Now, if you want to talk about something that's overhead intensive, that's hard to do, right? And you can imagine that not everyone does that in this kind of situation. And I don't know if anyone in the physics department today is actually doing those assignments. So people now are sitting wherever they want, which means if 2 good students sit together, they're done very quickly, don't help each other, and just move on. 2 bad students might sit together and no one's helping anyone, they're not helping each other, okay? So the way Scale Up was designed is not always the way that it's implemented. And that is perhaps an issue, because when Scale Up underwent very many studies about comparing the size of the table and the number of students at the table and all these different parameters they studied until they optimized everything. But that optimum experience included students who would read ahead of time, and it included students who would sit in these teams of 3, and it also included, I was recently reminded because we had someone come and speak to us about Scale Up from the university that invented it, and we were reminded of the fact that, in fact, in its design, the students in the team of 3 actually benefit from everyone in that team understanding. So if your student sitting next to you does not understand, you actually get better points, more points for helping that student, because your grade is tied somehow to the performance of that other student. In a small way, okay, not a huge part of the grade, but nevertheless, it's part of the grade, and many faculty find that really hard to swallow. I'm really going to give the good student a somewhat poorer grade because the person sitting next to them didn't understand. It's very hard to, as a faculty member, to kind of really go whole hog and just say, yeah, that's what I'm going to do. But that's how it was studied, and that's the way in which we know that it works. So we have now a situation where we teach these calculus-based classes in the scale-up room, and some of the students are not engaged. In fact, they're on Facebook or they're doing whatever. So that depends a lot on many, many factors, but I don't think in every case our scale-up classroom has 90 students sitting there who are fully engaged in the material. And so that needs, and so the question is, how does that compare to a regular lecture room where you're doing clicker questions and doing your best to keep them engaged? There's many factors involved. Anyway, this is what we do, and this is the status with Scale Up. Okay. You heard already in one of these provost conversations just recently in October about some recent innovations that Alex Goodenough has made. He was teaching Scale Up, and he really focused on the problem-solving aspect of getting students to learn. So he came up with a way to require students to keep a homework journal so that they wrote out the answers to their homework problems and went through several problem-solving steps. And only if they did that and handed that in each week did their homework get a full grade. So in other words, their online homework score was multiplied by some kind of check mark from that homework journal. If they didn't do the homework journal, they got a 0 on their online homework. So he has found very, very strong improvement in the students by doing that. And I think that gets to a very, very important point that rightly or wrongly, this online homework submission that we do is problematic. It's not always leading to the best possible outcomes for student learning. Why? Because it's reinforcing not necessarily good behavior but bad behavior. Of course, good students will always do well, and but if a student spends a long time just trying to get the numbers right and get that green check mark when they put a number in a box, then that is not quite the same thing as spending time. They're just so focused on that they don't spend the time writing and thinking and try to figure it out and asking for help. They don't spend the time going through all those steps that they should do to get the homework right. So his technique is essentially to have this homework journal, which kind of forces them to go through and write out solutions and think and figure out the problem-solving steps. And he has, as I said, he's seen a real improvement by doing that. And if you want to learn more about that, of course, he explained it all in one of these other provost conversations. He saw an increase in the A's and B's. He saw that D and F students were not helped. That's not extremely surprising. D and F students don't seem to be very motivated by grades in some cases, and so they're not going to respond to the requirement that they have a homework notebook necessarily. So, okay. Declan DePuer is here, and he also gave a provost conversation about what he does in astronomy. Now, this is a huge lecture hall, 400 students he has, and he has all kinds of different techniques to keep the students engaged in that lecture. They text questions to him while he's lecturing. He uses this learning catalytic software, which is another polling software that you could use, and he knows who's sitting in every seat, and he can answer, talk to them by name. I won't go through the details because he has spoken recently in this forum about what he does. His think, pair, share, shut up and calculate, quiet down and contemplate. Anyway, all these different techniques, all these things to keep the students doing something in class and not just having him lecture. Okay, so there's many different sort of variations in the way that you can engage students in the lecture itself. All right. Now let's move to algebra-based physics. That's the thing that I've actually taught myself. I never have taught calculus-based physics at ODU so far, so I haven't taught scale-up, but I have spent a lot of time teaching algebra-based introductory physics. And this is not taught in the scale-up method at ODU. We have large lectures, about 100 people. They take regular laboratories, 2-hour labs with about 30 students in them. And this course is taken primarily by biology and exercise science majors. Some of these students are not interested in physics. I think that's also true in the calculus-based sequence, but whatever. And most faculty who teach this course, they do involve the conceptual questions, and they have clickers in many cases. And so most people teaching this are doing conceptual questions. Some are doing more demonstrations than others. And that does vary from faculty member to faculty member. So what have I tried to do to improve this class beyond those usual things that we all do? One thing I've tried is to have graded clicker quizzes at the beginning of every class. I actually think this is reasonably effective. So the students, because I have the clicker, it's easy for me to deploy and grade a quiz in the first 5 minutes of class. I mean, that quiz is up there at time 00, and they have like 3 or 4 or 5 minutes to answer it. And there is no way of doing it if you come in late. So one thing that is my pet peeve that I find it very difficult to deal with is students coming in late. So I, of course, have not eliminated that problem, but it does make it a little bit less, because the quizzes are worth real points in the final grade. And I, again, keeping track of all those quizzes and, you know, who lost their clicker or used their friend's clicker. I mean, it's really hard to do that, but, you know, I think it's worth it. It causes the students to be there on time and to review their previous lecture, because I ask a very simple question based on the previous lecture. So if they were there and they were paying attention and they were aware during the previous lecture, they should be able to get that quiz question, you know, right reasonably often. So that's one thing I've tried that I actually am happy with, that I would continue doing. I also tried having extra problem solving sessions, because I thought, well, why aren't my students going to the Learning Center? They have all this help there available to them. I thought, well, maybe, you know, it would be more helpful if they could work together on the homework. So I'll have a special hour or two, I can't even remember now, where they just go and work with me on their homework. Could be like, I think it was, you know, 6 to 8 or something like that. I don't know what it was. But so I would try very hard to get the students to come to that. That way they can work together on the same homework, even if I'm busy helping someone else. And that's the idea in the Learning Center too. We hope that the students can work together so that while you're busy going around to other people, they are helping each other. But that doesn't happen as much in the Learning Center, at least as it could. So I found this to be useful for the students who attend, you know. And again, very few students attended. I would probably have about 10 at the most in a class of 120 students. And so not many students attended. It cost a lot of my time. I was helping the students who were already good and who were, you know, for the most part, were really, you know, the go-getters and seeking out all kinds of resources. But yeah, sure, that is a big help. You know, of course, I've also found if I sit individually with any student, I can help them, right? I mean, one-on-one interaction, one can help students. It's just, you know, it's a question of how to help them, as many as possible, in the most efficient time usage as possible. So anyway, I think I probably would not do that again, but I don't know for sure. I'm not teaching this class right now, so that's why I say I would or would not. Another thing I tried to do, because of my concern about the homework, is to have them hand in 3 homework problems to be graded, physically graded. So in other words, they have to write out the solutions of 3 homework problems. And that was also a tremendous amount of time. And it involved having like a half-time, or I forget what, a quarter-time TA or something, just to do that grading. Having those grades, I had to enter all those grades. I had to keep track of it. It was part of the homework grade. It was a lot of work. And of course, I don't know if it helped them or not, right? I mean, I have not taken the time to study these things or do some kind of blind test or whatever. So did that really help them? I just don't know. But it's a lot of time involved in that. But I somehow still feel like this homework issue is an important one for student understanding, and that somehow getting them to spend that time, like Alex Hudnoff has done, to write things down in that homework is important. Anyway, I tried that. I also tried assigning videos instead of reading before class. So I would spend all this time on Khan Academy going through all these videos of people that guy explaining momentum and all these different concepts. And I thought, well, the students will they'll watch a video even if they don't read the textbook. And actually, I think it's probably true that more of them did that than would do the reading. I think probably about 0 do the reading if you assign it, and probably some handful of the students did watch the videos. It was hard to find a video that was relevant to every lecture, and some of the videos on Khan Academy I actually thought were not very good, so I didn't assign them, and I sometimes tried to find other videos. But, you know, again, you can spend a tremendous amount of time. Once you found them, I guess you can use them, you know, for the next class. But I don't know that I would do that again. Anyway, so those are the things I tried, and I would say with very mixed success, because ultimately it comes down to there's good students who are probably going to do very, very well no matter what. How are any of these techniques affecting that middle group of students? I'm not sure. And then, of course, there's many students that are simply unmotivated by any, you know, attempt to to do some to have them do something different, as far as I can tell. So anyway, but that's what I tried. Another thing that I didn't try, but it's being tried now, is that we made this math in the same class, the introductory algebra-based class. We made a math remediation game that's been developed by a local company available to the students for free. The idea being that if they would refresh and reinforce their algebra skills, it could remove the impediments to learning the physics, because so many students have issues with math and with physics, and I'm not sure that it's always clear when it's a math problem they're having and when it's a physics problem. And so it's basically introductory algebra. It's regular algebra is what this review covered. But it takes several hours to go through that, depending on how many mistakes you make. I think it's probably a very, very good, it's both a game and an online version, so you can do either one, whichever you prefer. So we have 200 students taking introductory first semester algebra-based physics this semester. I think 40 of them went ahead and created their online account, and only 3 of them finished the full math sequence. And I'm sure they started it and thought it was boring. I mean, I have no doubt that it's boring to go through it. And I also think they already know the algebra. But when you look at the people who go through, and these are the ones who get all the way to the end tend to be the best students, there's many areas where they have real issues, and I do think it would be good for them to go through something like that at the beginning of the semester. But we did not make it part of the grade, and you can tell students if something's good for them. We all know that you can tell us all kinds of things are good for us, and we don't do those things. So, I'm not really, we all know that that's the way we all are, so I'm not surprised. But anyway, I think that if there was some way of requiring the students to do that, maybe it would be helpful to them. But I don't know. It's hard even to study it. It's hard even to do what's needed to study such a thing and decide whether it's useful or not. Okay, so where are we now? I really do think that we have the ability to engage students in lectures and to have them be more interested than they were, and to learn more about the concepts, and to generally have a better experience. I think we have that ability. I think motivated students can learn. They do learn. They probably learned before. So, maybe we've moved the needle a little bit on the middle group. I just don't know. I think the conceptual understanding of physics has improved in courses where the conceptual problems are given, like this one. I'm not sure about problem solving, and I would say that scale up is implemented very differently. I mean, it is part of what we do now, and it's implemented differently by different professors, and so it has good and bad aspects to it. It depends, is what I would say in that case, what exactly you do and who is doing it. Okay, so that's where we are now. Now I'd like to switch to a few aspects of all this that are worrying me or that I have concerns about, and my biggest one is this homework issue. Because I do think, but I don't know if I can back that up in any way, that it's the process of beating your head against the wall with the physics problems and trying to figure it out that's where you really learn the physics. And then if you circumvent that, as I think many students do, even good students, I think that really impacts learning. We have, as I said, the online homework I think is reinforcing this focus on just getting that number correct without understanding it and without having a written solution. And there's also cheating. I mean, what happens is you can actually take any physics problem and cut and paste it and put it into Google, and you will be taken to a website which shows you the formula and how to get the answer. So most students, whether you want to call it cheating or not, are doing that at most students. Many students are doing that. And there's such a range of activity in that sphere, right? I mean, on one end you might call it cheating, and on the other end you might call it, getting help. But it's a range, and I'm not trying to say it's black or white. I'm saying that if a student gives up too quickly and just goes online to get the answer, then there's no learning taking place. And so my fear is that we can do all these things we're trying to do in the lecture to make it more interesting and to keep the students engaged, but that if we do not solve this homework problem, I'm not sure how successful we can be. That's my fear. Again, I don't have research. So this is my first question for discussion, and I only have a few others. So I don't know what other departments expect from students in terms of homework in large introductory classes. I mean, maybe we're expecting something that's unreasonable. And what about small courses? And do your students meet your expectations? I mean, what do you think they should be doing for homework in a large introductory lecture class? This is my question. I don't know whether we need to change the way we think about it. So,
I do teach courses in which a number of the problems involve giving mathematical proofs and other kinds of problem solving. And one of the things I don't do is I don't equate the idea of online homework with simple fill in the blanks. Truthfully, I often give online homework submissions just to save myself from having to read the handwriting of many of my students. But what I often find myself doing is breaking down a problem-solving activity or a proof into the steps that I would take, and then formulating multiple choice questions for each of those steps to guide them through the overall structure of the problem solving, but require them to submit an answer for each of the steps, which gives me a little bit more feel into their process than simply what was the final answer supposed to be. It means that I still get the benefit of something that effectively grades itself, and let's face it, that's worthwhile too. But it also means that there's a built-in partial credit for how far along the process were they able to get. So, breaking something down in your demo here, ask explicitly what is the force imposed by upon the finger in the water, and get those component steps together. Those could still be asked, I think, in an online format, and would avoid some of the problems that you've described.
Now, do you give them more than one chance to answer those questions? Because that's what we do. So multiple choice questions tend to be
usually no,
just try
I
the
do
different
not.
choices.
No, I do not usually.
Okay, yeah, so I can see it. We actually do ask conceptual questions on our online homework, and we do break them down into steps, but we do give them multiple tries. So a question that's multiple choice tends to be a giveaway, which just doesn't mean it's not valuable, but that's an issue we face. I actually kind of like multiple choice questions on the online homework, but again, we find that if we don't give students lots of choices, or lots of tries, lots of attempts to get it right, that can also be problematic. But maybe we should rethink that. So, okay.
I have cell biology courses, and I use an online homework system from Wiley. And I don't just use multiple choice questions. I also incorporate essay questions into my homework, and they're also included on my exams. Unfortunately, that does mean that I have to grade, 120 essay questions times 2 per student, for each exam and each homework, which is a major pain for me. But I found that...
So you do the grading yourself?
Oh, yes.
Okay.
Oh, yes.
Yeah.
And it can be a lot of work, but a lot of times I'm usually looking for 1 or 2 keywords or key concepts so I can kind of scan their answers and get a very quick sense of whether they got there. And the rest of it, I don't have to read their answers necessarily in great depth to see if they got the concept that I wanted them to understand. My students actually do struggle more with the essay type questions, but they learn more from doing that. And some of them have actually commented back that they find those particularly helpful, or it forces them to think more than just multiple choice, because they'll just go through and they'll click A, B, C, D until they get the right answer if you give them multiple attempts at questions.
Yeah, yeah.
So if you do give them multiple attempts, I usually limit it to maybe 2 or 3 attempts depending on what I want them to get out of it.
How many choices there were in that problem? Yeah.
That too, yes, so that they can't just go through and keep trying until they get all the right answers. My students do find that really frustrating. They want to be able to get 100% on all their homeworks, and they get very angry if you don't give them the chance to get 100%. They feel like they have the right to earn 100% just by doing it multiple times.
Yeah.
What do you mean?
The hard work of doing it multiple times.
Yeah, but I tried really hard.
Yeah, right, I know it. I spend so much time on it. Our students spend a lot of time on their homework, they say. Yeah.
What I found I ended up having to switch to is using Blackboard tests or quizzes and assignments that I created myself, and forcing them to use Respondus Lockdown Browser. And that way,
Well, like what? Use what?
the Respondus Lockdown Browser.
Okay, I don't know what that is.
So that it's basically, before they even log into Blackboard, they have to open an internet browser that's available for everybody for free. It's on most library computers, and then each student can install it on their home computer or laptop for free through the university website. And it prevents them from being able to open any other windows, and it also prevents the students from being able to do copy-paste or screenshots. And of course, I had to come about this the hard way, because I found that many of them were just copying and pasting, and this is not even on mathematical problems. I don't usually give mathematical problems in biology. It's terms, definitions, examples, a lot of multiple choice, true, false, fill in the blank. And I tell them up front, it's open book. They can use their textbooks, they can use their
Sure.
notes. I don't care.
Yeah.
But they were still coming up with long lists of all of my questions that they were sharing with one another. So another option I had to do is I had to stop showing them the correct answer. I'd give them multiple tries on each quiz, but they would only know if they got a question right or wrong. They wouldn't know what the correct answer is.
So they couldn't tell their friend who was going to do it after them.
Right. I mean, unless it's true, false, in which case they would know, but, you know, for other things. But the Respondus Lockdown browser has really helped a lot, you know, cut down on their ability there. Now, the drawback is most students take their notes electronically. And so if you cannot open up your notes or an ebook, digital text, while you're doing the quiz, that would either require you to have paper notes, paper textbook, or have a second device, like a pad or their phone. But it's very hard to look at notes on a phone. And so I feel like it does, in a way, punish, you know, students who aren't trying to cheat. But it, you know, prevents the cheating for the 90% or so who would try it if they could.
Yeah, that's a very good suggestion.
I was teaching like a large introductory psychology class, like about 120 students for our department. That's large. And I spent a lot of time thinking about why, like, what can I do to help those students that are failing the class. And I started, like, the last time I was teaching, I implemented like an idea at the beginning of the semester. I'll have a conversation with them. What does it take to be an A student? Like, what does it take to be a B student and a C student? And how is that reflected in the different like tests or quizzes that they have? And
You would tell them that at the beginning of the semester?
yes, I'll ask them first, what do you think it takes to get an A?
Oh,
Give
yeah,
me
yeah.
some examples of how many hours are you going to work, and what
Yeah.
are you going to do, and how are you going to learn to get that grade?
Yeah.
And I'll ask them to give me those responses first. And then I'll go over and what I actually think they need to do to get those grades. And I saw that helped, like, definitively for the grades, like for
It did
that
help.
semester. Yes, for that particular semester, I saw like there were much more, like maybe less C's in the class.
Yeah.
And another thing that they did was, I helped them explain that multiple choice questions, there will be some that are requiring just memorization, but there will be others that require synthesis. So if they will only memorize a text, which they do, this is not going to get them the A. This might get them like a C,
Yeah, yeah.
but it's just, that's kind of like reflected in how the grades get computed. And then, like, I'll try to do at the beginning of the semester, let's say I do quizzes on a regular basis, and I see there are certain students that like did not perform well, and I'll send them a quick email, and I'll just like a very quick email to those students, and I'll say in the email, you fail that quiz. If you continue to fail, you're going to fail the class, but very early in the semester. So just kind of give them like an idea of a trajectory, like you're going a bad path. Like, so that's
Okay.
kind of like help with some of the students to come and talk to me and go over like, are they having some issues? So I saw like for some of them it did help. For others, of course, it didn't. I mean,
Right.
but at least I tried to give them some kind of like message.
Yeah.
Okay, I'm not
Yeah.
doing well. I need to start like
Yeah,
studying better. Yes.
interesting. Okay.
Since we did introduce this rather extensive early intervention program every semester for the 100, 200 level students, do we have any statistics that tells us how many students we can turn around if we catch them by these early grade reports?
Well, we do have now the EAB advising tool, which will flag those students who are not doing well along the way, and the advisors are notified to you know that you know Mary Jane or John is not doing well at this stage, and then they will intercede. We need more advisors to be able to make that really effective. So we do have that, and then you know moving to how effective it is, that we haven't had in place long enough to really measure.
I think this homework issue is related to motivation, and it sounds like you are getting at that a little bit. And of course, I also try to motivate them at the beginning of the course about how important the homework is and how you can't learn it otherwise. And I just don't know. And there must be some effective way of motivating the students to struggle with the homework before they type it in and look up the answer online. I would love suggestions on that, and on motivating them to take advantage of available resources. I said that we have many resources for them they don't take advantage of. And I also was wondering, it just seems like the students who are in that D and F category, they don't seem to be responsive to grade motivation, in the sense that it's hard to find something that would motivate them. And I wonder if it's because they know they can take the class again. I have no idea, but I just can't imagine why they're paying money for a class and completely resistant to all attempts to help them. And maybe I'm overgeneralizing, but that's still the way it seems to me, with some students. So
I teach that humongous astronomy class, and concerning the homework, I don't do it all the time, but a lot of the time I flip the classroom, which means tell students to watch a video of the lecture in their own time, and we do the homework in class.
A previous year's lecture.
No, I put up videos of me lecturing before the class, and they can watch whenever they want. But a lot of the problems that you've raised here are solved by the system I use called learning catalytics, which was actually developed by Eric Mazur, although he sold it to Pearson.
I didn't know that. Okay.
So, for example, if I send out a question to the class, the learning catalytics software groups the students by disparate score. So it automatically gets a student who got a good grade to text a student who got a poor grade on round one in order to discuss for round two, etc. So it does a lot of things like that. It takes care of all of the high maintenance aspects that you're talking about. You'd love it.
And that's because they use their own device in that case, so you don't have to have clicker numbers that are registered.
Yeah.
But what about the homework? I mean, don't they have to, is the
Well, they do the homework in class.
They do it in class.
So you can watch them. If my TA is walking around, and if they try to look up the answer, they'll get a tap on the shoulder. Talk to your friend. Don't go online.
I teach a large class, 100 students. The class is social inequality. And while students may admit that they don't know a thing about physics, they're all certain they know all about social inequality in the United States. And so I do quizzes, online quizzes with Blackboard. I try and do a lot of interactive stuff in the classroom. I'm shocked I never have much more than a third of the class actually taking notes during class. Like, they'll sit there with nothing in front of them to actually take a note, which just shocks me. But one of the things I have tried to do is and I've just discovered this, start talking about them. Homework is practice. None of us get better just by thinking about something. Most of the time we have to do it. And I love the way you said that sometimes the way to learn physics is to beat your head against the wall. Well, that's practice. I mean, what you're saying is
it's a fun thing to learn.
Yeah, you keep doing it over and over again. Well, I think that's true of anything that we're doing. And somehow we all want to, we get tired and we don't want to have to do all this work all the time. The students are no different. And the only thing I can think is that, like, everything has to be graded, even if it's a minimal grade, so that they feel like, okay, it's worth something. Because if it's not graded, if it's not going to be on the test, it's not worth anything. So they've really got into this belief system. I think we've done it to them with high stakes testing, is that the only thing that counts is that stuff that's going to be tested. Mm-hmm. So,
yeah.
But I'm finding that the more I grade, or even if it's a minimal thing, that gets response or involvement somehow.
I think I'm going to try to find a way of grading the reading ahead of time if I teach this again. I just think it's needed.
Speaking to the question of how to induce students to take advantage of available resources, let me ask, where is your physics learning center physically?
It's on the second floor in kind of this lobby-ish type of area, like a little.
And
it's in a common area.
Where are the rooms where the students actually take their classes? Is it in the same building?
Same building. It's in the same building. And a lot of the physics majors like to hang out there and also do work there.
So, I mean, the hangout part is important. Our department is currently split with between two buildings, and half of our faculty in one building, a smaller number of faculty are in another building where our classrooms and most of our computers are, and where the students hang out. And one of the things we've noticed is that even with something like faculty office hours, if I teach a section of a course and a faculty member whose office is in the other building teaches another section of the same course, and we hold office hours at the same time, the one in the building where the students hang out already will have lines outside their door, and the other person will basically be sitting there twiddling their thumbs alone in their office for that time. So physical accessibility to the students seems to be a really critical aspect of getting them to take advantage of almost any resource. If they have to trek over to another building, that's already enough of a barrier to keep most of them
I
out.
totally see that, and of course ours is in the building, but that's how we sold it to the faculty to spend their extra time on this in the first place. As we said, you'll have less time needed to spend in your office because the students will go to the Learning Center, and you know they'll come and see you sometimes, but they'll get their help from others. You can help many students at once, but again, not everyone takes
But apparently it's not enough.
Yeah. So. Okay, one more slide. I know we have to go. Or worry is that I'm starting to feel like we spend a lot of effort forcing students to do the things they're supposed to do. And we're coming up with, and I've heard some great suggestions, and I may actually adopt those suggestions, things that we can do to force them to do what they're supposed to do. And I completely agree that we need to work as hard as we can to help these students, but I wonder if we go too far, or if there is if at some point we go too far to accommodate the fact that they won't read a textbook and they won't do their homework or pay attention in lecture. I mean, and that's not my, I came to that concern because I was talking to a colleague at JMU, and I was making the usual statement about how lectures don't work. And we just say that. It's like, it's like you would never question it. And he said, wait a minute. Is it really a case that we can't expect a student to hear something in lecture and listen to it and understand it? I mean, are we really going to the point where we just simply stipulate that we just don't do that? And I'm worried that we have come up at least close to the line on all this stuff.
I happen to be teaching a class that I've never taught before right now, and I'm totally blown away because the students come to the lecture, they're there before the lecture begins, they are full of questions, and all I'm doing is lecturing. I'm not even doing anything of all these
Who
wonderful
are these mythical
methods.
students? What class are you teaching?
They're physics,
Yeah, okay.
and not only
Yeah.
computer science and engineering. So obviously it's the subject matter, right? Because that's the only thing that's different from my own experience, from your experience, with any. If the students are truly interested, yes, they will come to lecture.
But that's a physics major class you're talking about, right? You're talking about a physics major class.
Well,
A class for physics majors.
It's
right?
actually a cross list. So as I said, there are math, computer science, other students like that in it. Yeah. But the other thing I think we have to realize is that there is a large fraction of our students who play a very, very rough zero-time game, right? They have.
I know it. Yeah.
Every minute they spend on a homework for physics, they cannot spend on something which, at least in their mind, is equally urgent.
I know.
And they don't have enough time in the day. And I'm totally out of any ideas how to help these particular students. And I really don't know.
I know. Many of them are facing serious time challenges. That is for sure.
Why not get rid of general education courses? I mean, they were designed prior to the internet, when students needed to be exposed to a wide range of topics. Our current students are exposed to the entire world on the internet. They don't need general education.
And I suppose I still hold to this ideal of making a better rounded individual. But the thing is that students, although they have access to these resources, they aren't necessarily in science classes. They're not going to go take English classes to learn how to write a scientific paper. So then it becomes incumbent on us to teach them those skills in addition to all the other biology knowledge and content and subject specific matter that they do need to know, in addition to skills that they should be developing in other areas to become successful, like functional whole adults that can actually have a realistic career in their fields. They have to have some math skill, they have to have some writing skill, and the ones at least coming into my classrooms don't. I do think that we have some problems with time crunches, as has previously been mentioned. I try to be cognizant of that for my students. I tell a lot of my students, I know you're taking organic chemistry at the same time. I realize you're spending immense amount of time doing homework for that class and studying for that class, because I did when I took organic chemistry. That's all I did for a whole semester. I took physics at the same time. I did no physics homework and a lot of organic chemistry homework. I'll be honest about that one. Fairly easily, actually, because unlike a lot of students, I did learn from lecture. I have to hear someone else explain things to me, or I don't understand. I don't have a chance of reading a textbook and understanding it because it's dry and it's boring and I fall asleep like most of our students would if they tried to read the textbook. To me, that's part of what lecture is for, is to help explain how and why things are relevant and to show that these are things that you can be interested in, even though I know that I hated my nutrition class. It was a gen ed requirement. I thought it was ridiculous, but I still tried to find something that I could relate to my other classes to at least keep me halfway engaged. That was my perspective as a student.
But you had strong self-engagement and self-motivation.
No,
So
I was
students
lazy.
like you are easy. Oh.
I'll be perfectly, I didn't want to go home and do homework. So the more I could squeeze out of my in-class time, the less time I had to spend at home doing other things. So it was, I guess, about maximizing time, although I wouldn't have called it that then. I just thought I was lazy. So.
In the context of trying to get the students motivated and a lot of these other problems, I think we have to look at what's happening in high school, because we are getting students here and they are being prepared for college by the experiences that they've had before coming to college. And I suspect that a lot of these experiences are different from the experiences that many people in this room had. Now, there are probably other issues as well, but I think we're trying to solve a lot of these problems, and we try to do it in the context of the college experience. But I think to really be effective, we have to really understand how the students are being shaped, how they're being molded, how they're coming to appreciate that you have to work hard in order to learn. They seem to know this for sports. They understand you can't just watch someone play football and then you know how to play football. But if you try to convince them that the same thing is true of physics, somehow it doesn't translate. So in terms of getting them to succeed in academics, I think we have to be working with the high schools, or at least understanding what's happening in the high schools. And then just a second comment about grade forgiveness. I agree that should be looked at. I think it is a problem. More and more I see students whose attitude, when you tell them, you alert them that they are doing poorly, they're going to fail the class or do very poorly, that it's very nonchalant response. That's okay, I'll just take it next semester. And in fact, I hear anecdotally that some of the students will purposely do poorly if they're getting a C or a C+, they'll purposely do poorly so that they can lower their grades, so when they take it for grade forgiveness, they have a chance of having the second grade count. They don't appreciate that first poor grade stays on their transcript.
Or that they paid for it.
Or
I mean, that's the first thing.
They don't seem to care about that either. So.
Okay, I think we have to wrap up, but I would be very interested in further tips and suggestions if you have them for me after we take off the mics. So thank you very much for coming.